Hello learners, welcome back. I am Rajat Tiwari, lecturer, University Teaching Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai, and your subject matter expert for this course. In today's session, we will be exploring the topic of leveling, focusing on correction due to curvature and refraction, and the topic reciprocal leveling. We will delve into the critical aspects of leveling, specifically addressing the correction necessary for curvature and refraction to enhance the accuracy of your measurement. Additionally, we will explore reciprocal leveling, a method used to minimize error over long distances. In this session, we will be discussing firstly about the correction due to curvature, correction for refraction, the combined correction, and the reciprocal leveling. So, what is curvature correction? Basically, in leveling, the line of sight through the instrument is assumed to be straight line, which is unaffected by refraction. However, the true level line is curved due to Earth's curvature, with its concavity facing towards the Earth. When conducting leveling over long distances, the horizontal line of sight from the instrument does not coincide with the true level line due to the curvature of Earth. This curvature causes the reading on a leveling staff, which is held vertically, to be higher than they would be if the Earth were flat. This discrepancy necessitates the application of a curvature correction to achieve accurate measurements. Now, so what is the effect of curvature? The effect of Earth's curvature on a staff reading is the vertical distance between the line of sight and the level line at the point where both intersect the staff. This effect increases with distance from the instrument, meaning that over longer distances the curvature's impact becomes more significant. Now, we will see the derivation of curvature correction. So, in this figure you can see, let ABD be a level line through A and O be the center of Earth. A is the instrument position and AC, that is the line of collimation, will be a horizontal line. R is the radius of Earth. The curvature correction CC, which is equal to in this diagram, will be BC, from B to C. Now, the square from Pythagoras, OC square will be equal to OA square plus AC square. We can convert OC into R plus CC whole square, which will be equal to OA. OA will be your R square and AC will be your D square, the horizontal distance. Now, R square plus 2R into CC plus CC square will be equal to R square plus D square. Solving this, CC multiplied by 2R plus CC will be equal to D square, from which we can calculate CC. CC will be equal to D square divided by 2R plus CC. Since CC is very small as compared to the radius of the Earth, so we can neglect CC in the denominator. So, equation will be CC will be, that is curvature correction will be D square upon 2R. Now, taking the radius of Earth as 6370 kilometer, we can calculate CC as CC will be 0.0785 capital D square, where D will be the distance in kilometers. Since the curvature increases the staff reading, the correction is therefore subtractive. You have to learn this. True staff reading will be equal to observed staff reading minus 0.0785 into D square. Now, we will be dealing with refraction correction. So, what is refraction correction? The line of sight provided by a level does not remain straight. It gets bent towards the earth due to refraction. As it passes through layers of air of different densities, the effect of refraction is therefore opposite to that of curvature, and the points appear higher than what they actually are. You can see in this figure, the correction of refraction is always added to the staff reading. Let the line of sight affected by refraction be represented by AE in this figure. The staff held vertically at C actually reads at CE. Under normal atmospheric condition, the arc AE may be assumed circular, whose radius is 7 times that of the earth. The effect of refraction is therefore 1/7 that of the curvature, but of opposite sign. The correction due to refraction is always additive. The correction for refraction will be equal to, that is CR, that is correction for refraction will be equal to 1/7 into d square upon 2r. Solving it, it will result in 0.0112 into d square, where d is in kilometers. Now, adding both this correction, we will get the combined correction. Since the effect of curvature and refraction when combined is to make objects sighted appear low, and the overall correction is subtractive. From the above equation, we know correction for curvature is d square upon 2r, that is negative, and correction for refraction, that is 1/7 d square by 2r, that is positive. Therefore, the combined correction due to curvature and refraction will be equal to d square upon 2r minus 1/7 into d square upon 2r. So, solving this, we can get 0.0673 d square in meters, where d is in kilometers. For note point of view, the following points should be noted. Firstly, for ordinary lengths of sight, the error due to curvature and refraction is very small and is generally ignored. Secondly, the error due to curvature and refraction can be eliminated by equalizing the back sight and foresight distances, that is by balancing the sights. Thirdly, the error due to curvature and refraction can also be eliminated by the method of reciprocal leveling, which we will be seeing, and we will be dealing it in our later sessions. Now, the next topic is distance to the visible horizon. Let C be the staff station. As you can see in this figure, BC will equal to small h, it is the staff reading, and D be the distance of visible horizon. Let the horizon meets the earth's surface at A, the point where the level line CA meets the horizon of the point B. From our equation we know, or from the combined correction we know, h is equal to 0.0673 d square, where d is in kilometer. So, d can be calculated as d is equal to root over h upon 0.0673 in kilometers, or d can be written as 3.855 root over h in kilometer. So, in above equation, both the curvature and refraction correction are taken into account. So, our next topic is depth of the horizon. Let A be the point of observation at an altitude h meters above B, which lies on the level line BC. Let AE be a horizontal line to the point of observation A and perpendicular to the plumb line AO, O being the center of the earth as shown in the figure. The angle EAC between the horizontal line AE and the tangent AC to the level line is known as the dip of the horizon. The dip of horizon is equal to the angle theta subtended at the center of earth by an arc BC. So, the dip of horizon will be equal to angle EAC, which is equal to theta, which is equals to angle BOC. It can also be written as arc BC divided by the radius of the earth in radian. The radius of the earth being very large, the arc BC may be approximated to chord BC, which is equal to small d. Hence, the dip of the horizon in radian can be written as d upon r, where d and r are expressed in the same units. Now, let us take some examples. A level was set up at a point O and the distance to two staff stations A and B were 150 meter and 250 meter respectively. The observed staff readings on station A and B were found to be 2.725 and 1.855 meters. So, we have to find the correct difference of levels between station A and station B. So, as you know, the combined correction for curvature and refraction for the staff reading on A will be equal to 0.0673 into d square, which is equal to 0.0673 multiplied by 150 divided by 1000 into or whole square. We have converted 150 meter into kilometers, as d should be put in kilometers. So, it will result in 0.0015 meters. Next, the combined correction for curvature and refraction for the staff reading on B is equal to 0.0673 into d square. So, we will put d in kilometers. It is equal to 0.0673 multiplied by 250 by 1000 whole square, which is equal to 0.0042 meters. Therefore, the corrected staff reading on A will be equal to, as discussed in the previous slides, it will be equal to 2.7250 minus 0.0015, which is equal to 2.7235 meters. And the corrected staff reading on station B will be equal to 1.8550 minus the combined correction for curvature and refraction for the staff reading on B, that is 0.0042, which will be equal to 1.8508 meters. Therefore, the correct difference of level between A and B will be 2.7235 minus 1.8508, which will result in 0.8727 meter. Moving on to the next example, where we have to calculate the combined correction for curvature and refraction for a distance of firstly of 5 km and secondly for 500 meters. So, for the solution, first we will take 5 kilometers. So, combined correction is given as 0.0673 into d square, where d is to be put in kilometers. So, it will be equal to 0.0673 into 5 square, which is equal to 1.6825 meters. In the second question, that is of 500 meters, we know the formula for combined correction as 0.0673 into d square, where d should be put in kilometers. So, we will convert 500 meter into kilometer and we will put in the formula, which is equal to 0.0673 multiplied by 500 divided by 1000 whole square, which will give result as 0.016825 meters. Moving on to the next example, where a lamp on the top of a lighthouse is visible just above the horizon at a certain station at the sea level. The distance of the top of the lighthouse from the station of observation is given as 50 kilometers. We have to find out the height of the lamp above sea level. So, let A be the point of observation and B be the bottom of the lighthouse of height h. So, due to the combined effect of curvature and refraction on the top of the lighthouse just appear above the horizon. So, that is h will be equal to 0.0673 into d square, where d is in kilometer. Therefore, H will be equal to 0.0673 multiplied by 50 square, which will result in 168.25 meters. Therefore, the top of the lighthouse above the sea level will be 168.25 meter. Moving on to the next example, here it is given or we have to find out the difference in elevation between 2 points A and B. A level was set up on the line AB 50 meter from A and 1300 meter from B. A and B being on the same side of the instrument. The readings obtained on staff held at A and B were 0.435 meter and 3.950 meter respectively. We have to find out the two difference in elevation between A and B. So, the curvature and refraction correction are applied only if the observation are taken for a length greater than 200 meter. Therefore, the corrections are not applied to the staff reading at A. The combined correction for curvature and refraction is only applied to the staff reading at B, which is equal to 0.0673 into D square. So, D will putting in kilometers, which will be equal to 0.0673 multiplied by 1.3 whole square, which will result in will result in 0.1137 meter. Hence, corrected staff reading at B will be equal to 3.950 minus 0.1137, which is the reading obtained on the staff held at B, that is 3.950, and minus the combined correction. It will result in 3.8363 meter. So, corrected staff reading will be 3.8363 meter. The two difference in elevation between B and A is 3.8363 minus 0.435 meters, which will result in 3.40126 meter. So, moving on to the next example, the captain of a ship just sees the top of a lighthouse 75 meter in height. If the eye level of captain was 7 meter above the sea level as shown in the diagram, we have to determine the distance of the ship from the lighthouse. So, referring to the figure, firstly the distance AB, as you can see in the diagram, which is equal to D1, can be calculated as root over h upon 0.0673 from the curvature correction or from the combined correction, which is equal to root over 7 upon 0.0673. Now, for the distance D2, that is BC, it is equal to root over h upon 0.0673. So, as we know, the height of the lighthouse is 75 meter. So, we will put the value of h there. So, combining both the D, that is D1 plus D2, we can get the distance of ship from the lighthouse. So, it will result in 43.58 kilometers. So, the distance of ship from the lighthouse is 43.58 kilometers. Moving on to the next topic, that is reciprocal leveling. It is the operation of leveling in which the difference in elevation between 2 points is accurately determined by two sets of reciprocal observations. This method is very useful when the instrument cannot be set up between 2 points due to an obstruction such as valley, river, etc. And if the sights are much longer than ordinarily permissible for such long sight, the error of reading the staff and the curvature of earth and the imperfect adjustment of the instrument become prominent. Special methods like reciprocal leveling should be used to minimize these errors. In this method, the instrument is set up near one point, say A, on one side of the valley, and a reading is taken on the staff held at A as shown in the figure. Near the instrument, and on the staff at B on the other side of the valley. Let these readings be small a and small b respectively. The near reading A is without error, whereas the reading B would have an error due to curvature, refraction and collimation. The instrument is then shifted near to B on the other side of the valley, and the reading is taken on the staff held at B and that on A. Let these readings be C and D. The reading C is without error, whereas reading D would contain an error E due to the reasons discussed above. Let H be the true difference of elevation between A and B as shown in the diagram. So, in the first case, that is in the figure A, H will be equal to B minus E minus A, whereas in second case, that is in the figure 2 of B, H will be equal to C minus D minus E. Adding both above equations, 2H will be equal to B minus A plus C minus D, which can also be written as H will be equal to 1 by 2 B minus A plus C minus D. So, it is the error, we can write it as E is equal to 1 upon 2 B minus A minus C minus D. In the above derivation, it is assumed that the effect of refraction is the same while making observation from both the stations. However, if only one level is used, there will be a time lag in transferring the instrument to the opposite bank, during which time the value of refraction may change. Therefore, to ensure better results, some surveyors recommend the use of two levels, one at each bank, so that the sites are taken simultaneously. Although this will give better result, but each level may have a different collimation error. The instrument should therefore be interchanged and the entire procedure repeated. The mean of the four values will be the most probable difference in the level between the 2 points. Now, let us take some examples to clarify it more. Firstly, in this question it has been given or referred to the reciprocal level taken with only one level. We have been given the instrument station A and B and staff readings on station A and station B, and some remarks are also given in which the distance AB is being given as 800 meters and the reduced level of A is being given as 450 meters. So, in this question we have to find out the true reduced level of B. Secondly, we have to find out the combined correction for curvature and refraction, and thirdly, we have to find out the error in collimation adjustment of the instrument. Moving on, solving this, we have to first find out the true RL of B. So, instrument at A, firstly the incorrect level difference between A and B will be equal to 1.630 minus 1.03, that is the staff reading on B minus staff reading on A when the instrument station is at A, nearer to A, which will result in 0.600 meters. Now, when the instrument is at B, so incorrect level difference between A and B will be the staff readings on B minus the staff readings on A, that is 1.540 minus 0.95, which will result in 0.59 meters. Now, the true difference of level between A and B will be equal to mean of the two incorrect differences. So, we will mean it, that is the first value is 0.6 and the second value is 0.59. We will mean 0.6 plus 0.59 divided by 2, which will result is 0.595 meter, which will show the fall from A to B. The result can also be obtained by using the expression as H will be equal to B minus A plus C minus G upon 2, which will equal to 1.630 minus 1.03 plus 1.540 minus 0.95 whole divided by 2, which will be equal to 0.595 meter. Secondly, we will find the combined correction for curvature and refraction. So, as the formula of curvature and refraction, which will be equal to 0.0673 into d square. So, we will put d in kilometers. So, it will be equal to 0.0673 multiplied by 800 divided by 1000 whole square, which will result in 0.043 meters. Thirdly, we will find out the error in collimation adjustment. As we know, reading of A is equal to 1.03 meter, and also we have find out fall from A to B is 0.595 meter. So, the required reading of level line will be equal to 1.03 plus 0.595, which will result in 1.625 meters. So, the actual staff reading at B touching the horizontal line will be equal to 1.625 plus 0.043, that is the combined correction for curvature and refraction, which will ultimately result in 1.668 meters. So, but the observed reading at B is 1.630 meter. Hence, we can find out error in collimation adjustment, which will be equal to 1.668, that is the actual staff reading minus the observed staff reading, that is 1.630, which will result in 0.038 meter. Hence, the error of collimation is negative since the observed reading is less than the actual. In the last example, we have been given the nodes referred to the reciprocal level taken with one level only. We have to find out the true reduced level of B, secondly the correction for collimation, thirdly the correction for refraction, and lastly the combined correction for curvature and refraction. So, we can find out the true reduced level of B. Firstly, at the instrument, when the instrument is at A, incorrect level difference between A and B will be equal to 2.724 minus 1.425, as discussed in the previous question also. It will result in 1.299 meters when the instrument is at B. So, incorrect level difference between A and B will be equal to the staff reading of B minus staff reading at A, that is 2.504 minus 1.429, which will result in 1.075 meters. So, the true difference of level between A and B will be equal to mean of two incorrect differences, which is equal to 1.299 plus 1.075 divided by 2, which will result in 1.187 meter. So, in secondly, we have to find out the correction for collimation. As we already know the collimation error as 0.003 divided by 150 meter as given in the question. Now, we also know the distance of AB as 1150 meter. So, collimation error would be 0.003 divided by 150 multiplied by 1150 meter, which will result in 0.023 meter. So, the correction for collimation will be equal to minus 0.023 meters. And lastly, we will calculate correction for refraction as error due to curvature is given as 0.0785 d square, which is equal to 0.0785 multiplied by 1.15 whole square, which will result in 0.104 meter. Correction for curvature is minus 0.104 meter. Let the correction for refraction be CR, but combined correction for curvature and refraction would be equal to minus 0.104 plus CR. So, the total correction for collimation, curvature and refraction would be minus 0.023 minus 0.104 plus CR, that is correction for refraction. So, the correct staff reading at B with the instrument at A would be equal to 2.724 minus 0.023 minus 0.104 plus the CR, which will be equal to 1.172 plus CR. This must be equal to the calculated true difference of elevation between A and B. Hence, 1.172 plus refraction correction, that is CR, will be equal to 1.187. From this we can calculate refraction correction as 0.015 meters. And lastly, the combined correction for curvature and refraction can be calculated as minus 0.104 plus CR. It will be equal to minus 0.104 plus 0.015, that is the refraction correction as we discussed above. It will be equal to minus 0.089 meters. So, the combined correction for curvature and refraction would be minus 0.089 meters. So, dear learners, we have reached the end of today's session. I hope you find it informative and engaging. Thank you for engaging in this class. See you in the next class. Thank you.